C, we will be giving an overview of Unit 2 in the AP Physics C curriculum on Newton's laws of motion. So these are the main things, is of course the Newton's three laws. You have Newton's first law, which is inertia, Newton's second law, which is force and acceleration, and Newton's third law, which is the interaction between objects and the equal and opposite forces that you see. And then smacked in the middle, we have circular motion. So first law of motion. These are the key items that we need to understand about that. First of all, we have being able to just qualitatively explain Newton's first law of inertia. Objects at rest stay at rest, objects in motion stay at motions, but apply it to all these different kinds of situations that you have. An object will go in a straight line if there's no net force acting on it. And it will keep its same speed doing that, or it will not move. And you do need to understand relative motion as well. Second thing is that you need to be able to calculate forces with this concept. So the key idea here is that in both the x and the y direction, the forces, the sum of the forces, if something is in equilibrium, is zero. And this is when you really see, and Newton's first law applies in all situations. But if there is no net force on there, then there is no acceleration. The object will maintain its speed, whether it's not moving or moving, in the same direction when it is in this equilibrium condition. Because of this, if there are multiple forces, you can calculate one of the forces based on the other one. This is the condition for equilibrium, is down here. And you may have to resolve forces if you have, for example, an object that is in equilibrium, but there are three forces at different angles on it. You would have to resolve those forces and in their components to be able to do that. The x's are going to equal 0 and the y's are going to equal 0. So that all relates to this concept of Newton's first law. The big one, though, is Newton's second law, as you can see from the amount of points that you have on it. So this is the law I call of acceleration. Acceleration is caused by a net force, but it is tempered by mass. Mass is related to inertia. So in Newton's second law of acceleration, we will write this down. This is the big law that you will see over and over and over. You need to understand this formula, that the sum of the forces in whichever direction we're talking about, one dimension, two dimension, and all of stuff, is mass times acceleration. What are the forces? What is the mass that's going to cause the acceleration? That is going to be one of those big questions that you are going to ask yourself over and over in these different things. So I would, even if you get stuck on a problem and you don't know what to do, write down this formula here and try to figure out what forces are acting on it. So you have to describe an object, whether it's in equilibrium or in an acceleration state. Those are your two options, equilibrium or acceleration state, in different situations. So if it's going down a hill, incline. If it's going down a hill in equilibrium or acceleration, be able to describe that. If it's going down in equilibrium, there must be friction or some other force, like a tension from a string. If it is falling, maybe it has air resistance, and maybe there is no air resistance. So you should be able to explain that. Atwood's machines, if you remember that this is anything where you have a rope, you're going to see this over and over. And so with masses on it. So those are what are called Atwood's machines. It could be modified or not. Circular tracks, so circular motion applies to this as well. So with Newton's second law, big thing is you have to find the A, calculate the acceleration. You have to use the net force, so sum of the forces. Sometimes that gets tricky. Like the most common one, not a relatively easy one, is the elevator question. If the elevator is accelerating up, or down, what is the net force? Well, if you're sitting in here, you actually have two forces on you, and we sometimes forget that. You have, and you often say one. You have your mg, and then you have the normal force of that thing. And when you calculate your acceleration, you have to consider both of these forces. You have to consider the normal force and the mg. It's easy to forget the normal force. So calculate the average force in 2 dimensions. So you got to do it in 1 dimension and in 2 dimensions. Describe a trajectory that could be projectile motion, but it could be a hockey puck on on ice or something like that. What is going to happen if the force is perpendicular to its motion? So if it is moving at some speed, v, and then it gets a force perpendicular to it, what happens to the motion of the object? So be able to describe that. Of course, it's going to curve, but it's going to curve quadratically. Derive expressions for net force, and this is very key, is identifying all the forces and making sure you're clear on what those are. Like we did over here. What is the net force in the elevator situation? Well, it's the normal minus mg. And that is going to be causing the acceleration of the elevator. So write out Newton's laws expressions for inclines, elevators, pulleys, Atwood's machines. These are just examples, but those are very common examples. Free body diagrams, be able to do that. The black that I drew here is the forces on there. So I am guaranteeing that on the AP test, even though you have 2 questions, one of those questions is going to be drawing the forces on an object. So calculate unknown forces from the free body diagram. If you needed to know the normal force, you could use the free body diagram to help you get that. All right, so the acceleration and doing all these forces and everything like that, this is a big thing. We spent several months on this topic. So friction. Friction applies to Newton's second law. So you need to describe the relationship between friction force and the normal force. So our friction force is the coefficient of friction times the normal force. And so you have to be able to identify what the normal force is. It's our fun equation. It could be static coefficient of friction, or it could be kinetic. It's going to cause the friction, and you have to understand what those are. In fact, I probably shouldn't write the static. I'm going to write kinetic, because in static, you should have a less than or equal to. So distinguish between static and kinetic. So static is when there is no slipping. Kinetic is when there is slipping. Know what situations to use with each one of these things. Use the friction equation. So I'm going to write this. This is our kinetic friction equation, and our static one, it is less than or equal to the coefficient of static friction. And this coefficient of static friction is always greater than the coefficient of kinetic friction. Describe the direction of friction forces, which seem obvious, but sometimes you have to think about it. For example, if a car is going around a corner on a street and it's not slipping, it has friction force. Is the friction pointing up the incline or down the incline? Well, it depends on how fast the car is going. And so you have to be able to describe that effect. Derive expressions for force, for mass, force, angles, if there's friction conditions. And we do have our incline question. Remember our vectors, that x is usually associated with the cosine of theta and y is with the sine of theta. But with friction or inclines, we always switch it. Our normal force is coming straight out like this. And then maybe our friction force is upwards on. If it's trying to slide down, then our friction force is going to be upwards. And we have to flip. The friction force is going to be, or we have an mg force and we have a normal force. The mg on the box, you would have to consider it as mg sine of theta, even though it's in the x direction. And the normal would be the cosine. So flip those coordinate systems for that. And then these last 3 here are particular ones that we haven't really discussed at all, but derive the expression of drag forces. So the drag force, or the air friction force, is dependent on velocity. So it's some value times velocity. So that's what our friction force is. That velocity dependence actually messes things up, because depending upon how fast you go, you're going to change it. And you have to use what's called differential equations to solve it. But that is a situation which I'm going to address in the next slide. But you should be able to describe, for terminal velocity, for that case especially, if an object is falling, it has an mg force on it, and that mg force never changes. But then it will have a drag force. And that drag force at first is 0, but then as it picks up speed, then that friction force gets bigger and bigger and bigger till it finally hits the terminal velocity, where the mg and the friction force, the drag force, equal each other. And you could set your drag force equal to your mg to figure out what speed that is that happens. So calculate the terminal velocity. You would have to set the drag force equal to mg, because terminal velocity is when it no longer accelerates, when it's in falling. All right, differential equations of motions are a little bit different, and this is where we're going to be using some sort of calculus that we haven't really learned, and you're not going to learn it in calculus class unless you take a more advanced. This is our equation of, this is our Newton's law expression. Well, force in these cases is often going to be expressed in terms of velocity or position. Let's say that the force is dependent on velocity, like the drag force that we did. I'm just going to use that as an example. If that's the case, then you have to, for acceleration, we are going to use the k times velocity. We're just using this as an example, and you're going to use for expression, you're going to use the derivative of the velocity, because it is a part of, it's on both sides. Then to solve this, you would separate the variables. We have two variables. We have v and we have t, and you'd want to separate those two in order to solve this. So this is what's called right here an equation of motion. We have it in terms of velocity right now. You could have it in terms of acceleration or in terms of position, but those are what are called equations of motion. It describes the motion. So use this second law to derive a differential equation of motion. Solve the differential equation to figure out the velocity. Now, solving this is a little bit tricky. Bring the v over here, bring the t's over there, and then do the integral on both sides to solve that. I'll give you examples of that as we start to prepare closer to the test. So separation of variables, that's separating the v's and the t's. And then once you calculate the function of velocity, you can use that to get position and acceleration in our normal way. All right, next, another big one is circular motion. There's a lot of points here. I'll try to describe these. So there's really two kinds of circular motion that you really have a lot on. You have horizontal, and then you have vertical. The difference, horizontal gravity is always the same. In vertical gravity, the gravity effects are different in what they are doing, because in horizontal, it's always in the same direction. In vertical, the gravity works downward when you're at the bottom of the loop, and it works outward when you're at the bottom, and it works inward when you're at the top. So uniform circular motion means you're going around a circle at a constant speed. And horizontal is the easiest, and you can calculate the velocity. If you know how fast you're going, or what your RPMs are or something like that, you can get the velocity. But then your centripetal acceleration and velocity dependence. So your centripetal acceleration equals m, or not m, that's force We're going to get to that in a second. It's v squared over r. You should be able to get the centripetal acceleration as well with omega. Your force, your centripetal force, then is mass times acceleration. So mv squared over r. Okay, so those are your expressions that you are going to be using. And you can get velocity, or you can get acceleration, or you can get force. And sometimes you may even get r or mass. So calculate the centripetal force, calculate the radius, the speed, the acceleration of an object moving in a circle using these equations. Draw a force diagram on this. Always the net force, if it's in uniform circular motion, is going to be towards the center of the object. What is that force, though? Is it tension? Is it friction? What is causing it to go in that circular motion? So identify the forces. Describe the forces in horizontal, vertical, or if you have objects going in different circles. So you have an object going in a tight circle, an object going in a big circle. Be able to identify the differences between those. So that's more describing and not calculating. Direction, for an object moving in uniform circular motion, the velocity is perpendicular or tangential to the circle, and the acceleration is towards the center or radial in the circle. So to describe expressions, you can use polar coordinates sometimes to do that. Calculate the resultant acceleration of an object and for an object changing speed. So now this is where we have tangential and circular acceleration. You have to use vectors to do that, and they're perpendicular to each other, so you just resolve those two vectors into a final vector. Your acceleration, the resultant acceleration or force is going to be the square root of the centripetal force, the centripetal acceleration squared, plus the tangential acceleration squared. Okay. Drive minimum and maximum speeds for vertical. So if you're swinging something in a vertical direction, like say you're swinging a bucket over your shoulder, then what is the speed at the bottom? What's the speed at the top? You'd be able to get maximum minimum speeds using these expressions that you would have to do. You'd have to calculate all the forces and know that the net force is going towards the center depending upon the speed of the object, and then you can get the speed. And then the banked curve. That is a special condition where an object is going around in a circle on a banked curve. You have both the normal force and you have friction force that are causing the centripetal acceleration. So which one is it? You might have some friction force, you might have some normal force that's pulling it towards the inside, but there's a bank, and so it's not solely it's the cosine and the sine of those forces that is causing the centripetal acceleration. All right, and finally, Newton's third law is the law of interactions. So be able to describe forces in an interaction, no matter what kind of object it is. The moon going around the sun, what are the forces in that interaction? A ball sliding or a box sliding down a hill, what are the forces of interactions? And there's always two. There's pairs of forces, your action and reaction forces. They're not actually pairs, they're actually the same force, but they're acting on other different objects in opposite direction. So anytime there is a force, it's always a pair of forces, and it's an interaction between two objects, you need to be able to identify those forces. Describe the motion of objects that are constrained together by friction or strings or something like that. Lots of examples of this, but what if you have two boxes on top of each other and they're accelerating? Well, you got friction, and you have these different things that are holding them together, and you have to be able to describe that. Another classic one is you have strings that are holding onto these boxes. You have to figure out the tension in the strings when the whole system starts to accelerate. Okay, so all of these have to do with Newton's third law. And then expressions and constraints for multiple objects in a system. You could have, for example, a this kind of a pulley system, and you have an object down here, and you have an object up here. They both, one accelerates down like this, one accelerates this way. Those accelerations are the same because they're constrained together by the string. So being able to derive these expressions. If there is no rotational inertia on this, the tension on the tension of the string down here and the tension of the string up here, that is your interaction force, and they are the same forces in opposite directions. So when you have systems of objects, you have to consider all of these things. And that, I believe, is our lesson, our unit on Newton's laws of motion. It's a big one.